Start with first principles. Hydrogen is the smallest molecule, it diffuses quickly, and it exploits weaknesses you didn't even know you left in the system. That means the materials you pick, metals, elastomers, surface finishes, and welding procedures, aren't an afterthought. They define your leak rates, safety margins, compressor runtimes, and OPEX. Take a simple example. A ball valve spec for natural gas might look similar to one marketed for hydrogen, but a hydrogen-rated design will pay attention to stem sealing technologies, seat materials, and tolerances in a way that reduces permeation and fugitive leak risk. Those tiny differences become huge when you scale to hundreds of valves across a plant running 24/7. In hydrogen service, metallurgy matters. Austenitic stainless steels like 316 of a liter are common, thanks to corrosion resistance and good low temperature behavior, but grades and heat treatment still matter when you're dealing with embrittlement risks, especially in high pressure applications or when cycling temperatures. Nickel alloys and specific surface finishes can minimize diffusion paths and improve long-term sealing performance. If you're moving to cryogenic liquid hydrogen, tougher material challenges appear. You must consider ductility at very low temperatures, thermal cycling, and differential contraction across dissimilar metals that can open micro leaks if the design is sloppy. In short, there is no one-size-fits-all metallurgy for hydrogen. The service envelope dictates the bill of materials. Let's talk valve types and where they shine. For isolation service in gaseous hydrogen at high pressure, ball valves with live loaded stem packing and metal-to-metal seats are popular because of low pressure drop and robust shutoff. For throttling, globe valves outperform because you can actually control flow without chewing up seats. Where you need zero dead volume and ultra-clean operation, think fuel cell grade hydrogen or analytical lines, diaphragm valves are the gold standard, especially when you pair them with electropolished tubing that minimizes adsorption and contamination. Check valves look simple, but hydrogen challenges them too. You need cracking pressure and spring selection that avoids chattering and pressure shocks, plus sealing materials that won't embrittle or outgas over time. Sealing is the next battlefield. Many elastomers that live happily in natural gas service will disappoint you with hydrogen. Swelling, permeability, or rapid gas decompression damage can show up fast. That's why developers lean toward perfluoroelastomers in some services, or, better yet, eliminate elastomers where possible using metal gaskets, metal-seated valves, and double ferrule compression fittings optimized for hydrogen. The goal is to make the leak path as tortuous as possible and remove diffusion-friendly materials from the wetted path. Even the surface roughness of a ferrule bite or a tube end face affects micro leaks, which is why certified installers and orbital welding procedures become non-negotiable at scale. Speaking of fittings, many of you ask, should I weld or should I use compression fittings? There's no universal answer. Orbital welding gives you a permanent, low leak joint with excellent cleanliness, perfect for long runs and critical paths to the compressor or storage banks. But a plant is a living organism. You'll be swapping analyzers, adding instruments, and isolating subsystems for maintenance. Quality double ferrule fittings allow modularity without compromising leak integrity, if they're installed to spec with the correct tube hardness, wall thickness, and preparation. In practice, most developers mix both, weld for high-pressure backbone and use fittings for instruments, skids, and points of change. The wrong mix shows up later as a commissioning headache when leak checks drag for weeks and your schedule slips. Safety and standards tie this all together. The quickest way to derail a project is to ignore applicable codes. It's boring, but essential: pressure equipment directives, materials traceability, fire and area classification, relief device sizing, vent stack routing, and hazardous area electrics. You need valves with pedigree, certifications, hydrostatic test records, and, ideally, hydrogen-specific qualification data. The best teams create a standards matrix early: which valve series meet the pressure class and temperature range, which fittings are qualified to the cleanliness spec for downstream fuel cell or ammonia synthesis. What documentation package do you need for lenders or insurers to accept the design? If you leave this until procurement, you'll find yourself redesigning with long lead times and cost overruns. Cost control lives in lifecycle thinking, not part price. You can always buy a cheaper valve. The question is how often you want to shut down, depressurize, replace packing, leak check, and ramp back up. Hydrogen punishes maintenance shortcuts because every restart is a safety event, a production loss, and, if you're grid connected, an opportunity cost against time of use pricing or curtailed renewables. The ROI of higher grade materials, better stem packing, and ultra-clean tubing is realized in fewer leak events, faster commissioning, and tighter purity that protects catalysts and downstream processes. In economic terms, think like a project financier. CapEx delta of a few dollars per valve is irrelevant compared to multi-day outages or lost offtake penalties. Let's put this into a practical mini-spec a developer can use as a starting point. For a 20 MW PEM electrolyzer plant delivering 350 to 700 bar gaseous hydrogen for mobility and industrial users, select isolation ball valves with hydrogen-rated stem seals and metal seats for the high-pressure header, backed by globe valves for pressure control stations. Use diaphragm valves and electropolished 316 liters tubing in the purification and analysis lines. Standardize on double ferrule compression fittings qualified for hydrogen with documented tube hardness windows. Enforce torque and makeup procedures via installer training and signed ITPs. For storage manifolds, prioritize welded joints, leaving fittings only where modular swaps are expected. Specify instrument vent valves and test ports so leak checks can be executed quickly without disassembly. Build a cleanliness spec that covers oil-free handling, nitrogen blowdown, and particulate testing before first hydrogen introduction. Now add the water and temperature reality. Electrolyzers don't like contamination, and valves on the water side must be compatible with deionized water and cleaning agents. Avoid creating particle traps near the stack. If your site experiences freeze-thaw, you need drain points, heat tracing, and insulation that doesn't cook your elastomers. In hot climates, stem packing materials face thermal aging. Choose ratings with margin and design shading or ventilation around hot surfaces and compressors. And consider oxygen service too. Your O2 line needs compatible materials and oxygen clean components. Never assume hydrogen ready equals oxygen ready. Commissioning is where theory meets plant. Plan a progressive leak check from nitrogen to helium to hydrogen where appropriate, with acceptance criteria defined in advance. Tag every valve and fitting with a digital certificate, serial number, heat number, material certs, so your maintenance team can trace issues in minutes, not days. Create a punch list culture where installers log torque, make up turns, and any rework immediately. You'll thank yourself later when a pressure decay test fails and you can isolate the issue to a single joint without guessing. Finally, don't underestimate the narrative power of this invisible engineering. When you're pitching off-takers, investors, or authorities, showing mastery of valves, fittings, and standard signals that your team understands hydrogen as a system, not a headline. It reassures everyone that safety, uptime, and purity are designed in, not bolted on. The components you choose today directly influence your LCOH tomorrow, through leak losses, maintenance intervals, and product quality that protects catalysts and compressors. In other words, the smallest parts can have the biggest impact on bankability. If you want real hydrogen projects that work in the field, start by getting the hardware right, and it begins with valves and fittings. If today's breakdown helped, check out the resources linked below. The course gives you the full project lifecycle. The LCOH model lets you stress test design choices like premium valves or welded joints, and H2 Hub Premium connects you with practitioners who've solved these problems at scale.